going to be presented by Andreas Fender, and this is co-authored with by David Lindlbauer, Philipp, Herholz, Marc, Alex, Jörg, Müller at TU Berlin. Take it away.
All right, thank you, Andy. So the work I'd like to present today is called HeatSpace. So my name is Andreas Fender, and the co-authors of that work, Andy listed them already, David Lindlbauer, Philipp, Herholz, Marc, Alex from TU Berlin, and my supervisor, Jörg Müller. So the problem we are trying to explore with this is the fact that information displays are often placed by intuition. So if we're looking at that image, for example, of a cafeteria's entrance area, we can see a display in the upper right corner, which is visible in principle, like you can see it, but the people in that space are mostly busy with picking up their trays and cutlery and so on, so they're not necessarily looking at that display. And so it's important that the installer actually knows how the space is used in the end, and that's often not the case. And that's also true for other environments like in a manufacturing domain or in office spaces. So the idea we have is that we let uninstrumented users interact in the physical environment doing the normal everyday routine. And while they're doing so, we measure their viewing behavior, and in the end, our system automatically proposes display placement based on these measurements. So and this is what it looks like. So first we capture the environment and we do some 3D reconstruction. And then we let users interact in that environment and we measure the visibility while they're doing so. And we're reconstructing the physical environment based on static surfaces and moving objects. And we also built an application where installers can try out potential display positions and get real-time feedback. And finally, we optimize the placement of these displays. So what we're contributing with is an empirical analysis of user viewing behavior and an optimizer for position and size of displays. And the overall goal is to replace guesswork with quantitative measurements. So these are the components of HeatSpace, and I'd like to go through each of these in detail. So let's start with capture. So before getting into the details, I'd like to show the example setup that we used. So we were using 3 depth cameras, Connect 2 devices, and they were all positioned so that they were seeing the scene from an orthogonal angle. The area of the space is 4 meters by 4 meters, and we used various different furniture arrangements for the different examples. So the capturing is pretty straightforward. So we're using the feed of the depth cameras to reconstruct the physical surfaces, and then we're generating real-time meshes based on these depth cameras, and they serve as a point cloud and also as colliders for raycasts, which is going to be important later on. And we're also using the built-in skeleton tracking, the Kinect SDK's built-in skeleton tracking for user viewpoints. So the second and one of the core components of the system is, of course, the generation of the heat maps. And first of all, I want to mention how we actually store the data. So we're using voxel grids, which are just uniformly distributed in space. And each of these voxels are storing local data about different aspects, which I'm going to explain in detail right now. So each voxel is storing, first of all, the persistence, the distance, and the visibility. So let's start with persistence. So persistence means how static an object is. So we can see, for example, in that little video that the whiteboard is pretty static and the table. And the reconstruction, we can see the reconstructed static surfaces and which have a high persistence. And then we have medium persistence objects, which are moving objects, and these are indicated with these white glows and that rendering. And then we have a distance. This one is pretty straightforward. So we're simply measuring, for each voxel in space, we're measuring the distance from the user's viewpoint to the voxel. And in that image, we can see that the table close to that stylized user is very like orange, which means that it's close, and the wall and the background is a bit farther away, and therefore it's green. So visibility is a bit more sophisticated and like kind of the most important measurement we do. So with the visibility is just a measure of the quality of that voxel, like how well visible is it for a user. And we are splitting it into 3 components, the first one being occlusion, then we have the field of view and the viewing angle. So occlusion simply means for that instance in time, is the voxel actually occluded or not? Is it visible from the user's point of view? And if there's a physical surface in the way, in the line of sight, then the occlusion is 0, or the value is 0, and otherwise it's 1. So the field of view is decreasing whenever the angle between the user's view direction and the line of sight between the user's head and the voxel, which is depicted as L, is increasing. So we're getting the user's view direction simply by using the face tracking capabilities of the Kinect SDK. And so that just means the further in the peripheral the voxel is, the worse the quality gets for that voxel. And viewing angle is taking the surface itself into account. So let's say there's some geometry within that voxel, and that geometry also has a surface normal. And then we are simply measuring the angle between the line of sight and that surface normal to get the viewing angle. So what that means is that when you're looking at a table, for example, with a very narrow angle, then the quality of that measure is really bad. And if we're looking straight at a wall, for example, then the value for the viewing angle is very good. So in the end, we're multiplying all these things to get our visibility. All right, so all these measurements are calculated at each moment in time for each frame. And what we do in the end is we are time accumulating them. So the persistence and the distance and the visibility each are time accumulated. So for example, this is the visibility for the first instance in time, where we can see like pretty much like one focus point, but over time it's getting a bit more distributed, and over time we're getting we are finding out which areas are getting more attention, which are getting less attention. And I'd like to talk about like one of the implications, in particular about occlusion. So for example, here we see a user interacting at a table. And for that instance in time, we can see on the table there's the occlusion is either 0 or 1, depending on if it's occluded by the arms or not. But over time, we can see that, that the whole area is kind of bad quality, even though they're not occluded in that instance in time. So that means that displays would be positioned further away from the user, even though the viewing angle and everything is nice. But still, since the hands are always like waving in front of the user, it's still a bad surface area, for example. All right, so the last big component is the display placement. So the way our application is structured is like that. So first, the installer needs to specify some displays. So there are some parameters. Some of them are optional, some are required. And so the first parameter is the number of displays. So that's a value that the installer has to put in. And also for each display, the resolution has to be set. And optionally, the installer can kind of try out some initial positions for the displays. And optionally, the size can be fixed, or it can also be delegated to the optimizer to optimize the size of the display, if that's a degree of freedom for the installation. And in the end, based on these values, we want to find optimal display surfaces. So, and this is what the application looks like. So we can explore the reconstruction, and the installer can just freely position some potential displays anywhere in the room, and then set some parameters and move the displays around. And while the installer is doing so, he or she is getting real-time feedback. So within the displays, we can see different shadings indicating how good that portion of the display can be seen. and also the quality is being output. So the displays can be positioned on any static flat surface, which can be vertical or horizontal. And if it's horizontal, then the display can also be rotated. So and finally, after the installer has set up some initial positions, the optimization can be triggered simply by clicking Optimize. All right, and I want to briefly talk about the optimization algorithm. I don't have time to really go into detail, but I just want to provide you an idea about how we're actually doing the optimization. So the first step is to find planar and geometrically persistent candidate regions. And the way we do that is we're creating a connected components graph, and that graph is based on persistence and planarity. So that means, for example, if we're having a flat table and a whiteboard, which are like close to each other, then these two are two different connected components. Even though they're physically attached, they still have a different surface normal, and therefore they have two different connected components. So the second step is to sample potential display positions. And then for each display to be optimized, we do the following. So we're placing the display greedily on the sample with the highest score where there is no display already. And now that step is kind of important. So if displays end up on the same connected component, we're using an alternating gradient descent approach. So this means, for example, if there's like a big wall or a big whiteboard, whatever, and two displays are positioned on that big connected component, then it would be kind of unfair for one of the displays if we first optimize the first display and then the second one, and then the second one has to figure out some other space somewhere close. What we're doing instead is putting them both at the same time on that big connected component, and then gradually, locally optimizing both of them at the same time. So that's the alternating gradient descent approach. But of course, way more details in the paper. So also I'd like to show some example results. So in that first example, we are having two users sitting at a big table. And what we can see here is that the second user is blocking the view to the wall for the first user, which is also reflected in the real-time feedback. And of course, the optimizer is taking that into account and is moving the display so that the occlusion is kind of minimized. We can also see two smaller displays to the right, and even though they are kind of in the peripheral of the first user, the resolution requirement and the size requirements forces these displays to be really close to the user. So the second example are two users sitting opposite each other. And what we can see here is that the first user has a pretty good overview of the room behind the other user. However, if we are looking at the combined heat maps of both users at the same time, then we can see that only in the peripheral for both users, which is like the wall to the right, can actually be used for displays. And then the optimizer is, of course, taking that into account and positions the displays so that they are visible for both users, not only for one of the users. So, of course, we're having some limitations, some of which we're also trying to tackle in the future. So first limitation is that displays have to be attached to static surfaces. So what we mean by that is that for example, we cannot use ceiling suspended displays or displays which are just standing in the middle of the room. Because if we would use these displays, then they would change the whole physical layout of the room, and all the occlusion patterns and everything would just look different. And therefore we cannot optimize these. And also, of course, there might be a behavioral change after installation. And this is especially true for interactive touch displays. So which means displays where the intention is to actually change the interaction and the workflow within the space. And therefore, we are more focusing on displays where the intention is to not change the workflow too much, to seamlessly integrate these displays into the workflow. So primarily information displays. Or otherwise, we can just keep measuring. So after an initial optimization, we can just keep measuring and maybe refine or verify the display placement. So to conclude, So the system I just presented is called HeatSpace. We're letting uninstrumented users interact in the environment, and while they're doing so, we are measuring persistence and distance and visibility, and these values are stored in voxel grids. Measurements are time accumulated, so they're measured over time. And the display placement optimization is based on that empirical data. And the overall objective is to replace guesswork with quantitative measurements. All right, and with that, I'd like to end the talk, and of course, I'm open for questions. Thank you.
Steve Feiner, Columbia University. I love work that tries to automate the performance of certain things that people would normally do by hand. I have a question, and this is something I encounter, and I know many other people encounter as well. You have a multivariate equation there that's going to determine the score for something. So what made you decide on the particular weights of the individual things you were combining together, and did you do anything to try to validate that they were the right way to do things?
Yeah. So this is kind of briefly also discussed in the paper, so it's a very good question, and also something we thought about. So these different weights, of course, right now they have to be set by the installer, and that requires some knowledge and maybe some intuition about how to weigh occlusion against peripheral field of view and so on. It depends on, for example, if the content is moving a lot, then it's maybe not so important that it's in the central field of view, because if there's motion, then we can kind of relax that condition about the peripheral field of view, and then the installer can kind of adjust the exponent for that value. But of course, in the future, it would be kind of cool to also explore setting these parameters automatically based on the content to be displayed. So for example, if we know that the content is animated, then we can kind of adjust the weight for the peripheral view. Or if we know that the display has a really bad viewing angle range, I don't know the exact word for that right now, but these old displays which are really hard to see from the side, it's not such a big problem nowadays anymore. But if we know that, then of course the viewing angle would have more weight, so to say, then that display has to be seen from the front, for example. So there's a lot to explore in that direction also.
And also doing studies, to see with a particular layout how people actually perform, to get a sense of which things really matter. One thing I noticed that didn't seem to be in there unless I missed it was if you and I are at opposite sides of the table and there's a display on the surface of the table and it's got text that we have to read, one of us may end up reading it upside down unless you sort of make both of us read it from the side. So did you try to take that into account, the orientation of the content?
Actually not yet, but that's a pretty cool idea actually, yeah. So I guess we only have that problem with horizontal displays, so maybe that's something where we need to investigate a bit more in detail how it works differently when we're kind of focusing on horizontal displays, when all these additional challenges have to be taken into account.
Yeah. Thank you.